All right, this has been a very quiet morning. Matt, can you say something? I want to make sure my audio works.
Yes, your audio works.
Well, I heard that, so yes, it does indeed. Thank you. All right, this has been a very quiet morning. Matt, it's been a very quiet. That's terrible for the recording right there.
Oh. So far, I haven't seen any suggestions of how to do the poster sessions. Did anyone have preferences on going in the first or second group? I'm going to take that as no, then I'll make something up during a pause. But I think the plan is we've got the 5 live Q&A talks, and then we'll have the 2 poster sessions, and Nick looks confused. And then, and then hopefully everyone did have a chance to watch the videos. Huge shout out for the Tamer video, 90s style infomercial was spot on. And let's see, so with that, we should probably get started. Let's plan on taking a break in about every hour, because, yeah. All right, so why don't I hand it over then to Brad to kick us off?
Hey, can you hear me?
I can.
Excellent. Okay, just give me 2 seconds here to get my screen share set up.
And then everyone, please remember that also on Saturday, I'd like you to have one thing that you liked about either someone's presentation or the research, and one thing that you thought that could be improved, again, either with their presentation or the research. And that's for the videos and posters, as well as the live stuff we're doing. So take it away, Brad.
Okay, and just to double check quickly, you can see this just fine?
Yep.
Perfect. Okay, so my project was software effort estimation with humans in the loop. So first of all, I'll just quickly explain software effort estimation. So it's a very important part of the software development industry. You need to have accurate estimations so you can project how much development will cost, how much time it will take. If you're doing work on a contract basis, you often agree upon the amount of time and the amount of expenditure that you have at the outset. So if you end up being inaccurate, you end up losing money in the long run potentially. And even if you're out on a contract, it can cause serious issues with your release cycle if you vastly overshoot your expectations. And this is from a study in Harvard Business Review. You can see that software projects tend to be very bad when it comes to accurately estimating the time and their costs. So there has been some research into finding better ways to do this using machine learning. Looking at a systemic literature review from 2020, just get some idea how the current research is going. The most common data sets being used are the COCOMO 2 dataset, the NASA dataset, and still a very significant chunk of them are using random or artificial data. And out of all of those, most of them are using either a multi-layer perceptron or a regression model, and a smaller number are using a wide variety of other methods. Problem with this, with the random artificial data, I don't see being very applicable to the real world. And when it comes to the COCOMO and NASA data sets, they have vastly too many fields to be reasonable for your average software development team. Most small teams are not working with knowledge of memory constraints, runtime performance. They don't usually have measures for every analyst capability, software engineering capability. This kind of data set doesn't exist for your more small teams. A more realistic data set that your average small development team has is basically just this. You have the title of the task, the category it falls into. You might have some simple things like the program area it belongs to, but mostly you have just a text-based description of the problem. And that's all you have to go onto for estimates. To actually try to turn this into a time estimate, one of the common methods used is something called planning poker. It starts off with the task description being led by the leader. Then there's a bit of a discussion. Every person estimating the time will pick a card secretly and then reveal them all at once, so you're not being influenced by someone else's opinion. After that, people discuss any outliers, and at the end, if there's a consensus reached, they go with that. Otherwise, some teams will just take an average if they can't agree. But this is what we're using, and it's still obviously not producing results that are anywhere acceptable. So my hypothesis is that taking this very basic task description data we have, I can extract a few categorical pieces of information from it directly into the learning model, but I can employ the human experts to do what they already are doing with Scrum Poker to pick their blind estimates at the time and feed those in as input to the learning model and potentially produce an improved estimate, perhaps. So I would theorize that this will produce a better estimate, actually. There is one study that worked on a very similar problem in recent years. They did it somewhat similar, but very different in some key ways. So they did look at the regular story card that I showed earlier there, but they would take the task description and actually perform token extraction on it to find the most common word tokens. They also did include the human estimation, but they included the final human estimation after planning poker resolved to a consensus. They didn't have individual per person values, which is what I'm curious about. And in their study, decision trees, including the planning poker estimate, was the most performant model. So going into my pilot study, the issue I have is no data sets exist, as far as I can find, that have individual per estimator values. Collecting new data would take far too long. The team I work with, we do maybe 10 to 15 tasks per week, and this had to be done within a few weeks. So historical task data was going to be re-estimated to provide enough data to work with. Which poses some problems, but it's the best I've got for a pilot study. So just to acknowledge the data set and the human experts were sourced from a local company where I do personally work, so should acknowledge that. The data set that I have to work with just has, as I mentioned, some very basic information. Has the category, the program area, a couple Boolean flags if the task requires formal design work before development starts, if it requires any unit tests to be added, then the actual time it did take, and the historical estimate that the team originally thought would be appropriate. There's also the title and description that will be going to the human estimators. And the data set entirely has over 3,000 tasks, and it is largely skewed towards short tasks. And the estimation values are just like the Scrum Poker values. They're only given in discrete values. We just try to estimate the time class it falls into, not the exact time it will take. So for the pilot study, I'll only be looking at that classification task, trying to determine which bucket it would fall into. But long term, it would be more interesting to determine the exact time. But just for the pilot study, stick with classification. The human participants is just a small team of 5 developers, myself excluded. There's one inexperienced developer who has under 1 year experience. The other 4 are over 5 years experienced in professional development. And the project the data set comes from has been under development for 2 years. So it's a very robust project. The developers are very familiar with it. It's not a brand new thing. From the data set, because I couldn't ask my coworkers to re-estimate 3,000 tasks for no pay, I only sampled 200 tasks, stratified to make sure every developer was equally represented in the dataset. And I made sure that every task I picked was at least 6 months old, so it wouldn't be too fresh on the memory, but that is still a threat to validity if they happen to have some residual memory of over half a year ago, which for me doesn't exist. But so yeah, just to put it back into perspective about the methodology here. So that's how the human experts will be producing these values, is using this program I wrote right here. Fairly rough, but it does the job. Has the title, category, area, description, and they would just click on what they estimate for time on the bottom. So yeah, so for models I considered, I looked at complement naive Bayes, multi-layer perceptron, decision tree classifier, and I tuned all of these with a cross-validated grid search. Complement naive Bayes, I'm sure everyone's familiar with naive Bayes, but just in case the specific one is new, it's an improvement on multinomial naive Bayes. It's known to perform better on unbalanced data sets, which is what I'm working with here. And try not to be too confusing here, but the way it works is by selecting the class with the smallest probability of not being the correct class. The formula on the bottom here, there's the regular naive Bayes formula where you find the argmax, whereas on this one you find the argmin of not being correct. The other one, multilayer perceptron, I picked this one because it's, as I mentioned earlier, the most common model in software estimation research. I went with current state of the art and using rectify linear activation functions on the hidden layer. And because it's a multi-class problem, I had to apply a softmax to the output function. Otherwise, it's your basic feed forward backpropagation neural network. Nothing else more special than that. And the last model was a decision tree, which I chose because in that related study, this was the most performant model. Just a very high level overview on how this works is as it goes through data, it will select the best attribute, use that attribute to create a decision node and break the data set into smaller subsets, and repeat this process recursively until all the leaf nodes are of the same attribute. So to validate that having the separate estimates is actually meaningful, I'll be recording data under 4 different modes. I'll be going without any planning poker data. Then I'll be including just the historical estimate. So it'll have the basic data and then just the average that we estimated the first time. Then I'll be using the averaged planning poker estimate from the data collection done now. And then I will also be doing finally with the per user estimates for each person, which is what I hypothesize will produce the best results. I also want to acknowledge that earlier in my study, I did experiment with doing 1 overall model and 1 model per estimator, but I'll address why that was a problem a bit later. So for my experimentation, I have 2 baselines for comparison. There's the historical estimate accuracy, as well as the average planning poker accuracy. So if I can't do better than what we did the first time ourselves, and if I can't do better than just averaging people's guesses this time, then obviously there was no real point to doing any machine learning here. So I won't reject my hypothesis if I can exceed both baselines, but also if the per user estimate mode outperforms every other mode for at least one of the models I'm training. For metrics, I'll be using accuracy just to compare against the old baselines. But for handling the fact that this is an imbalanced multi-class problem, I'll be looking at the F1 score for comparing the models together. So the results, I got results from doing stratified k-fold cross-validation across 5 folds, 20 repeats, shuffled of course. So it's 100 total runs for pretty good data to work with. The accuracy, as you can see here, the average accuracy over all 100 runs. Sorry, tongue-tied here. The historical accuracy was 65% and the new average was 66%. So we're fairly consistent over time. The only models that didn't fail to outdo these measures, though, was naive Bayes without the individual estimates. It's worth noting the individual estimates managed to push naive Bayes above that level. And it seems, at least at this point, the best performing model was the multilayer perceptron with the individual estimate planning poker. Looking just quickly at the average F1 score, again, tells the same story. The multiplayer perceptron was the highest. And to make sure that these are actually significant, I first checked to see if the data was normally distributed, which it did seem to be. So I used the ANOVA with Tukey post hoc analysis to see the differences were significant enough. And that gave me this. So going left to right, this color here is the naive Bayes models. The middle section is the multilayer perceptron, and these over here are the decision tree models. And on all four of the three of the sections, it starts off with without planning poker, then with historical planning poker, then with the new average, and then with the individual estimates given separately. So significant results here is in the case of naive Bayes, it did reject the null hypothesis in the case of the individual estimates being an improvement over having no planning poker data at all. So that was a significant improvement, but it failed to reject in both the case of the historical average and the new average. So in this case, it was pretty clear that the individual estimates provided a much more significant gain. Also, in the case of the decision trees, it rejected in all cases of without any planning poker data versus any case with planning poker data, but it did not reject between the different modes of providing that data. So for decision trees, it seems that it doesn't matter how it was provided as long as there is an estimate. But there's no significant difference between any of these three. But finally, in the case of the multilayer perceptron, it rejected the null hypothesis with everything that looked close to the MLP with the individual estimates provided. So it improved vastly over the same model with both historical and new averaging, and it improved significantly even over the tree with the individual estimates provided. So just quickly regarding that one model per estimate approach I mentioned, the issue that I encountered was that training was only meant to be done on tasks each estimator completed. My theory was that they would train a model to estimate themselves, and then the averaging of those models would produce a better overall accuracy at the end. But there wasn't enough data for each developer with each label. So once it was broken down and stratified, there were some cases of there being 0 to 1 instances of any given label, which made training pretty much pointless. So I decided it wasn't really worth looking at. So to reestablish the conclusion here, so this pilot study has demonstrated that combining planning poker estimates with task data does improve prediction. Per user estimate data does outperform the average alone. And of the models considered, the multilayer perceptron was the most performant. So for future work, I'd be looking at some broader data collection with exact timekeeping so I can move beyond classification and predict perhaps the exact time value. I'd like to collect more data and reevaluate the one model per user approach, because it would be a great way to build this in practicality, training a different model for every developer. And lastly, I'd like to investigate just how much data is needed before this model can begin outperforming human estimation. And that's everything. Any questions?
Sure. Hi, Brad. How do you think your model would handle outlier tasks, like things that are either extremely long? I know when I'm doing user stories and whatnot, I love to put big, gigantic, massive stories in there, especially when I'm at the start of a project and then they kind of get whittled down. Are you looking for kind of the final version of the story to run on, I guess is what I'm asking.
Yeah, I guess that's one thing I forgot to address. At least in the data set I was working with, tasks that are 2 days or longer are quite rare. So even though the data set that even though my sample did include a couple of tasks that were 4 and 5, like not 4 days, but 5 or longer, I counted everything as 2 days or longer as 2 days or longer. Again, just because the data set was quite limited, I didn't have enough data to try to estimate those longer task labels. So to answer your question, the model as I have right now strictly wouldn't handle that. It would just treat that as a large task. But future research, if I can collect more data, I would love to be able to estimate accurate values at any scale.
If you could pick any one dimension of new data, like for example, so having more samples or having longer term samples, like what do you think would give you the best results? What's your highest on your wish list?
Highest on my wish list would be data collected properly over time so that it's not tasks that the developers have already seen beforehand. I think that would be the most valid for proving this is actually a method that can work, because right now we might be seeing some effect of the developers just getting better at understanding these tasks since the last time in the case of accuracy. Yeah, I would say more data, but specifically more data collected fresh would be what I want the most.
Do you think your company would have any appetite for actually doing this or using this? Or do you think they would say, well, it's not a big enough improvement and we don't want to bother collecting more data because that's a distraction?
Well, the whole goal with the system I'm trying to build here is that if it's built correctly, it's almost invisible to the users, because we do planning poker as it is anyway, but for every task. There would need to be a program created to more smoothly collect those values in the same way that we estimate them. But with that system in place, we wouldn't even notice it, so they wouldn't even object in the slightest. And from talking to them, if I'm able to make a product that works well, they'd absolutely use it. But, it has to work first.
That's pretty encouraging, I think.
Yep.
Cool. Time for one more question, if anyone has one.
I was just kind of interested in knowing, because it looked like the inputs were all text. So was it you were just using one-hot representations, or did I completely miss what actual inputs were going into the models?
No, you didn't miss that. I kind of glossed over it. When it came to the categorical data, yes, I did use one-hot encoding. And when it came to the time values, I used an ordinal encoding. But yeah, that wasn't on my slides. You are correct.
Did wait, so did you use like the text description at all as inputs to the thing then? Like,
oh, okay, let me just go back to my little diagram.
sorry, maybe I just.
So yeah, the text description and title only went through the human experts. They were the
Okay. That's what I missed. Okay, cool.
Yeah, the one related project did use token extraction on the description, but one theory I have is that to do that, you'd require a lot more data to get up and running and make this predict usable results than in the case where you have just these discrete values coming from humans. So I think this will be a much more real world applicable model.
Yeah, so the humans were the natural language processors. I think that makes sense. Awesome. Thanks, Brad. Then I'm going to suggest we jump right into Delaney's presentation.
All righty. Let me just get this in present mode. Okay, so everyone can see what looks like the beginning of a presentation?
Yes.
Perfect. Okay, I tried to get this down closer to 10 minutes. It was a little harder. So if I go a little too speedy and you miss something, feel free to just note the slide number, and that's something we can go over in more detail in the Q&A. But other than that, my name is Delaney, and I'm going to be presenting my presentation on personalizing learning with sound hunters. So starting for a bit of context, this will be focusing on the language Plains Cree. So Plains Cree is what's known as the Y dialect of Cree, which is from the plains of Western Canada, including here in Edmonton, Alberta, where the U of A is. Cree was considered an extremely low resource language. So not a lot of language resources in general, let alone language learning resources. In the last census, there were self-reported approximately 96,000 Cree speakers. And of those Cree speakers, 3,600 identified their dialect as Plains Cree. So Plains Cree has two major writing systems, also known as orthographies. So the first one is what's known as the standard Roman orthography. It's an alphabet with 10 letters. Can people see my mouse? Or should I get the pointer? There we go. With 17 letters. So as you can see, some of the letters are similar to English. And some of them also make the same sound as their English counterparts. So M still makes an sound. That's not true for all of them though. For example, the K, sometimes it sounds like a K, sometimes it sounds like a G. So there's also syllabics. So this is a syllabary, which means that the symbols represent a syllable sound. But for the case of this study, we're going to be focusing on SRO. So what is Sound Hunters? Well, Sound Hunters is an arcade-style game that teaches phonological awareness in Cree language learners. So what that means is learners are better able to know the sound to character mappings. So this aids in being able to know how a word sounds, even when it's just being read. So this is useful, particularly due to most learners have a lack of access to speakers and recordings. So being able to know how to speak the new Cree you're learning is essential, and it's far more likely that you have access to written resources, especially through things like social media. So the game mechanics are players get given a sound on repeat. So with this is a repeating GIF, but they would be given the K sound. So a little pixel deer come down the screen with text attached to them. One of the deer's attached text is associated with the given sound. So this deer will be referred to as the target item. So the other on-screen deer will be referred to as distractors. So the player must use a little shooter here at the bottom to shoot the target item. If they shoot the target item, they get points, and a full points bar is a win. If they shoot one of the distractors, or the target item leaves the screen before they shoot it, they lose health, and an empty health bar is a loss. So in the original version, before I started this study, there's 4 tasks. So the first task is single letters. So as you can see in this first screenshot, it's just single letter sounds and text. The second one is letter pair sounds, so valid letter pair combinations in the language. The third is minimal pair words. So this is a minimal pair is 2 words that differ by only 1 sound. So an English example is fun and sun. In this example, we have minigueo and miniguec. And then the final one is words, so just distinguishing which word is which. So each task has 3 levels, easy, medium, and hard. The difficulty is determined by the speed at which the deer descend, the number of distractors on screen, as well as how distracting the distractors are. So I'm just going to focus on the first and second task because those are the only ones that are going to be relevant to how far this study got. But in the single letter task, actually for both of them, a distractor is considered distracting if it is audibly and or visually similar to the target item. So an example would be the short A would be a distractor for the target item, the long A, because the short A makes an sound. Sorry. And the long A makes an sound. So they sound relatively similar, and they obviously both look like A's. So why should we bother personalized learning with Sound Hunters? Well, the current version, although it's not identical through each play due to some aspects of random selection, it is relatively one size fits all. However, language learning is not the same for everyone. And this is especially true for learners of Indigenous languages who are often older and starting from different levels of previous knowledge. So how are we going to personalize Sound Hunters? We're going to implement something called user modeling. So this is where we try and model what the user does or does not know. And specifically, we're going to focus on constraint-based modeling. So a constraint is a declarative rule in a discipline that can be violated. So in math, if I do 1 + 1 is 3, I've violated like the additive constraint. So the value of constraint-based modeling is it tries to model what the learner does not know rather than what they do know, because it's a lot harder to prove and know whether someone actually knows something, where it's a lot better guess if they get something wrong that it's because they don't know it. So the constraints in Sound Hunters is relatively simple, and I'll try and go through this one slower because it's a lot of the same type of words. But if the player shoots a distractor or the target item goes by, they will have violated that target item's constraint. So for example, the target item was the letter E, and they do one of the two described, they will have violated the E constraint. So there's also something we have to consider called joint constraints. So for example, in subtraction, when you're learning subtraction, you learn how to subtract positive numbers, and then also you learn how to subtract negative numbers. Subtracting negative numbers requires knowledge of subtracting positive numbers, but failing to subtract negative numbers doesn't necessarily mean that you don't know how to subtract positive numbers. So basically, and again, a lot of words, but I'll have some examples. What this means in our context is successfully not violating a constraint where the distractors are dissimilar does not mean the player would not violate a constraint where the distractors are similar. So for example, if the target item was the short A and it had P and N as distractors, that would be where they didn't violate that constraint, but they did violate it when it had distractors with the long A and the short N. It wouldn't mean that, you know, we'd have to necessarily go back to that one. It would mean more that they can't distinguish between these similar letters. So in this case, what we define as a joint constraint would be a target item paired with a similar distractor. So the short A and long A. We also don't assume that they're commutative. So that means that if you're given the short A and you distinguish it between the short and the long A being the one with the hat, that doesn't mean that you could distinguish it between the long A and the short A, given the long A. And this is mostly just because we have no evidence to prove otherwise. These, as far as we know, these are separate tasks. So we're also using what's called stereotype modeling. So this is where you assume a stereotype about the learner. And it helps address the cold start problem. So it basically, in our context, it would help build an initial order for a new player where we have no previously collected data. And in this case, the stereotype we're assuming is that the player speaks English as either a first language or at least a primary language. And this would help initially prioritize letters whose sound is the same as like the English counterpart and move the player forward quicker. So the example I gave before is M. So now that means we have two versions of this game. So we have the non-adaptive version. Participants in the study knew it as the blue game, which is just the version, the version is the original version that I described. And then there's also the adaptive version, which was known as the red game. So this models the user knowledge as previously described, has the initial ordering based on the English stereotype. And then a user must successfully not violate a constraint twice consecutively in order for it to be like removed from the roster. So we chose twice consecutively because, as you can see, there are often there are 2 or 3 distractors. So 3 or 4 deer on screen at a time, which means you could guess. And so we want to avoid assuming that a constraint wasn't violated just by guessing. Yeah, so it helps avoid guessing. And then as well, the single constraints must be learned before the joint constraints. So with this, we're starting with a pretty basic research hypothesis, which instead of, comparing both exactly, we're seeing if the order in which the games are played, if we are able to see if there's a difference in learning game. So how this study worked is participants were split into 2 groups. The first group was given a knowledge pretest. So all the knowledge tests were where we asked the participants to transcribe Cree recordings, specifically 4 recordings. This was followed by gameplay of the adaptive or red game. So for each gameplay they were asked, participants were asked to play the game for 7 minutes each for a maximum of 14 minutes of gameplay. This was followed by another knowledge test, same idea as the first one, except for it's different recordings, followed by playing the non-adaptive or blue game for 7 minutes, followed by another knowledge test, again, the same except for different recordings, and finally ended with a questionnaire. And the questionnaire contained questions on demographic information, player experience comparing the two game versions, as well as just general open-ended questions about gameplay experience. Group 2 was exactly the same, except for in step 2, they played the non-adaptive one instead of adaptive, and then in step 4, they played the adaptive one. So for this, I got 6 participants, which were split into the two groups, as said, where group 1 played red and then blue, or adaptive, non-adaptive, and then group 2 did the reverse. Okay, so for the results. This is where we compared basically the percentage score improvement between the knowledge pre-tests and the knowledge post-tests of both groups. So what this means is the test that sandwiched the study, essentially, before they started playing, after they played both. Here, the red is the red-blue, so adaptive, non-adaptive, and the blue is blue-red, non-adaptive, adaptive, sorry. This is a very small sample size, cannot assume this is normally distributed. So we use the Mann-Whitney test to compare these two unpaired groups, which got us a p-value of 0.2, which is not significant by pretty much any measure. But we also had this effect size of 0.53. So within the context of a pilot study, it is useful in terms of like knowing that this is something that could be built on. What is kind of interesting though is I also compared the gains between games. So for each participant between, since each gameplay was sandwiched between tests, it was the percentage score gain between those tests depending on the game. And so this is kind of how it looked for all participants. Again, small sample size, so we used the Wilcoxon test to compare these two paired groups. We had a very high p-value, as well as a very small effect size. If you looked at the averages between these, like just flat out, they were very similar. So just on its own, very similar, which is not useful. And then as well, I documented some player experience, which is always useful because you can make the most, something that teaches you best in the world, but if no one likes it, it doesn't matter. So I asked which game they felt was better paced. Half the participants said the adaptive, the other half was split between non-adaptive and no difference. In terms of which was more challenging, half felt that the non-adaptive one was more challenging. In terms of more material covered, half also felt the non-adaptive covered more material. This one I'll touch on a bit more, but it makes sense because it was easier to move forward into like the next task. Whereas with the non-adaptive one, or sorry, the adaptive one, you had to twice consecutively get all these constraints, whereas that wasn't necessarily the case with the non-adaptive. In terms of which game they thought gave them a better sense of progress, pretty evenly split between one or the other or neither. And then in terms of which game gave a better sense of accomplishment, half said the adaptive one. So for future work, if I were to continue the study, I would like to have more participants, as well as longer gameplay time. So this study had a maximum of 14 minutes gameplay time, whereas the initial study that I did on the non-adaptive one before had a play time of up to an hour. So when we were measuring that kind of thing, it was a lot more significant gameplay, as well as exploring and trying to figure out how to balance the content shown within some amount of restricted time, even if we were to up it to like half an hour each, for example. Because like I said, the non-adaptive version allows the users to move forward, given just that they won the current level rather than that they've proven they know all single letters, for example. Whereas the adaptive version doesn't allow you to move forward unless you've proven that you know the necessary constraints. Similarly, if you recall the other writing system, Syllabics, it'd be fun to make a Syllabics version because it would be relatively simple. with little additional work. Just the distractors would need to be kind of well defined, which by extent would be defining the joint constraints. And in this one, the stereotype modeling would not be employed or applicable because there's no, you wouldn't be able to use any English knowledge transfer to syllabics because there's no relation between the alphabets. And that's everything. Thank you. I don't have Discord open, if there's anything there.
Questions?
Hi, Delaney. I have a question.
Hello.
How do you differentiate between a lack of understanding and whether or not they just missed the target? Because it's kind of like an arcade style game. Is there any, like, do you know the skill of the user at all?
So that's a really good question. And it's also something that's not currently legitimately implemented, but I could use the data from this type of study to figure that out. So there's no limit on like the amount of arrows that you get. So that would help mitigate a bit that it's been missed, but we do log if one was hit, that was the incorrect one. We do log the position of all of them. And so basically future work on this game overall would be actually really useful in the adaptive one, would be to try and have some type of mechanism to decide whether it was sufficiently close in some, axis, to just figure out whether it was a genuine misunderstanding or a gameplay mistake, because that's always an issue with game-based learning. And then there's also potential for just having like some either evaluate or just general practice with the game where it's not anything learning, like it's something, you don't have to guess, you just know exactly which one to hit, and you could potentially get used to the gameplay mechanics like that. So in short, no. In long, hopefully someday.
Sounds good.
Hi, Delaney. I had a question about how you evaluate people's improvements between like the pre-test, mid-test, and post-test, because I think they were different words, right? So how do you actually figure out if somebody's transcription ability is improving?
So with respect to the recordings, they are different. So you're not just, redoing the same one over and over again. But the idea is that they're similar. So it's going to be similar sounds and similar. Every now and then a word would be repeated. And so from there, we also have a specific type of like grading that I cut out of this, which is basically, since it's more about being able to tell whether they're starting to recognize the sounds. The grading system that we established from the last study was that if they got the letter right, so we weren't including spacing because that's not what we're teaching. If they got the letter right, they got a point. And if they got the letter close, they got a half point. So what that means is for the letters where there's a clear English counterpart, like, so for the K and G, they would get a half point like that because we knew they were actually hearing the sounds properly. And so it was graded based on that. And then there was the percentage score gain from there, if that answers your question.
Yeah, it does. What would happen if somebody were to have like two English characters that kind of sound similar to one Cree character? Would that be 0 points?
It would depend. We have it very specifically. We only have 4 instances where that happens. And that from there, it's kind of just judgment. That's honestly, in the last one, there were 2 of us who went and scored them. So at least had that kind of agreement. But if it seems like it was, like if it was 2 where it didn't quite line up with the ones that we have, like if it negated one, it changed the actual sound of it, then that would probably get 0 points. But there was nothing that got like negative points. So if you added in a bunch of letters, like it would depend on what sound you're trying to represent. It's a little bit of just best judgment.
Hi, Delaney. Any thoughts on how to add feedback to people on how they actually do on the assessment? If that makes sense, like I get that you're kind of grading it after the fact, but
That's a good question. I've never thought of that just because we don't do any real assessment within the game, like in terms of the actual game mechanics. It's only ever been strictly in the context of a study. I don't know if within the game it would be particularly useful. I think it would, how it would more kind of come to be is, this is part of a larger website that has like a number of things to learn Cree. So it's not supposed to really stand alone. Yeah, it's supportive in that way. So I haven't really thought of it in terms of like telling, evaluating based on that. There is this, I think this is kind of straying away from your question, but in user modeling, there is kind of like the topic of open user models, which is trying to show the user what you think they know. And there's a lot of pros and cons to that, especially because the user often doesn't have an accurate user model of themselves. So it can be useful in some ways of like, you need to work on this more, but it can also be confusing. So it's, in conclusion, kind of evaluation is hard in terms of something you're actually going to tell the user.
thanks, that makes sense.
I have a bunch of questions, but I think we should cut this off and move on to the next talk, unfortunately. But I'm going to bug Delaney with my questions later, and I think you should too.
Great.
Thanks for that presentation. And then up next is Scott, I believe.
Yeah, awesome. All right. Okay, everybody can see this, I assume. All right, so my presentation is non-expert labeling as additional supervision for medical image diagnosis. So I'm going to talk about some background and some related work, and then I'm going to talk about the existing model that I based my project on. And then I'm going to talk about my project, the modifications to it with additional supervision, the experimental methods, then the results and some discussion. So machine learning applications in medical imaging have been growing in popularity, particularly over the past 5 years. Medical imaging is comprised generally of 2 medical specialties: radiology, so the field of medical specialists that look at X-rays, CT scans, MRIs, that kind of thing, and then pathology. So pathology is the medical specialty that consists almost entirely of looking at slides of tissue under the microscope and then making a diagnosis. An enormous number of pathology specimens are breast cancer related, just because of how common breast cancer is. So to understand a bit of what's required for this and what the problem is, I'll go over a little bit of the current paradigm for early breast cancer, which is the majority of it. So the typical pathway that somebody would follow would be that they would have like a mammogram, or they would potentially feel a mass, and on a mammogram, there might be an abnormality like this one here. And then you would go on to get a mastectomy, either a partial mastectomy or a total mastectomy. This is a total mastectomy here. I've edited it for grossness. What a lot of people don't know about this is that there's an additional part of this surgery that's done on the vast majority, called an axillary sentinel lymph node biopsy. So here in the armpit, a lymph node is taken out. Usually it's between 1 and 3. And the purpose of this is to determine whether there's cancer in this lymph node. If there is cancer in that lymph node, then that goes on to affect treatment decisions. So this lymph node is taken out by the surgeon, and then it turns into a slide like this one, and it gets looked at under the microscope by a pathologist. The pathologist then decides cancer or no cancer, and that goes on to affect treatment decisions. Because of how common breast cancer is, this is just one slide. Like the whole thing is sectioned into many parts, and the whole thing is looked at under the microscope. It's very labor intensive, and there is huge opportunity for machine learning to improve workflow of pathologists and potentially improve patient care. So the problem basically boils down to an AI deciding whether it's a tumor or not. I don't know if I'm dating myself with this reference. Related work on this particular topic started out with the majority looking at small patch-based tasks. So either looking at a very small patch of tissue that has been labeled and then training a classifier to classify other small patches, or to do small tasks such as assigning the nuclei positions of different cells in a small patch. More recently, whole slide image diagnosis has been done, requiring detailed annotations. So essentially pixel-wise annotations of original slides that are then decomposed into small patches, and then a diagnosis is built back up. This requires extensive annotation, and an implementation of this is what my project is built on. But the eventual goal, and there's a few systems like this, is to do whole slide image diagnosis using coarse labels. So just what the pathologist would do naturally. They would say it's malignant or it's benign, and then having that be the only form of supervision. This is the eventual goal. And so the goal for my project was to see if we can create another bridging step in here, potentially with less data. So my project is based on Arjun Vekaria, his master's project, which was using a public data set of exhaustively annotated whole slide images. So where the tumor regions are completely bounded and defined by the data set by an expert pathologist, which is then used, broken down into tumor patches and normal patches, fed into a convolutional neural network, which is then applied to a test set, which creates a tumor probability map, which then spits out a final diagnosis. So the additional supervision that I had in mind, so for example, I thought that if you decompose, for example, this patch here, where the blue here annotates where there's tumor region, all the rest of it is non-tumor, this patch would be classified by Arjun Vekaria as completely benign, despite the fact that there are some cancer cells in here. And with some training, I thought most people could probably pick out that these abnormal looking cells here, including this one, are cancer, and the other ones are not. Sometimes this task is easier than others, but there's a lot of fuzziness in the data. There's a lot of areas where, for example, this is a cancerous cell here, and it's outside of the boundaries. So I thought there could be lots of places where the data, despite being labeled like pixel-wise by an expert pathologist, there might be room for improvement. Another example is here. So again, nominally, the data is entirely pixel-wise annotated, and it looks like the expert pathologist was carefully going out and picking out all of these little globules of fat, and then just kind of got bored here. And if, for example, the algorithm is picking out this patch and this patch, they would be classified differently, despite there being nothing qualitatively different about them. So I thought there's a potential for improvement here, even with complete novices. So my plan was to find the patches that the model does the worst job at classifying. So it creates, for each of those patches, it delivers a probability of how much it thinks it's tumor or not. And then I looked at the difference between that and the actual label. I picked the largest differences, so the models or the patches that the model did the worst job at classifying, and presented these to humans. for additional labeling to just straight replace the existing labels and then to be fed back into the convolutional neural network. So I recruited 10 semi-experts. I unfortunately don't know any pathologists that could be true experts to help me with this, but I found some non-pathologist MDs and then 10 novices, so lay people with no computer science or medical background to kind of simulate what it would be like if, for example, I used Mechanical Turk. I then found the worst individual patch predictions based on the probability heat maps, this being an example of a probability heat map where blue is close to 0 and red is close to 1 for probability of there being tumor. And then I showed these as well as the 8 surrounding patches to participants for further labeling, sort of like this. So this is contiguous for them. This was the patch that was selected in the middle here. And then they would go click and decide on new labels and then submit them. There was some minimal training that everybody had. I just showed them what some patches look like with tumor and which ones didn't. And for ones that they were unsure about, I just discarded them. So these in diagrammatic form, it follows the same process as Arjun-Beccaria's method, except that these new labels are then fed back into the deep model, which is then run on the test data once more. So I had each person do 50 trials for those 9 patches each, times 10 participants. These were fudged a little bit. Some people did a little more than others just because it was a bit of a boring task, and I worked it out, but I managed to get 4,500 new labels for each group for experts and non-experts. I have a little breakdown here of how much changed, which is potentially important given that, unfortunately, it's a completely negative set of results. So these are receiver operator characteristic curves. So this plots the false, oh, sorry, that was cut off here. This is the true positive rate by the false positive rate. So a coin flip would be the dotted line here. And the blue line is the original method of Beccaria, which is a little bit different based on randomness in, or from his actual thesis, based on some randomness in the model and some undefined parameters from his code, and then compared it to the curves for the experts, the non-experts, and then I put them all together just to see if having some more data would help. So the p-values using the DeLong method are all extremely non-significant, unfortunately, for how these perform compared to each other. So it does beg the question is,
Scott.
Yeah.
Would you mind just pointing out what the y-axis was in that last picture?
Sorry, it's the true positive rate. I'm sorry that got cut off.
Thank you.
Oh, right. So perfect. I guess I could mention, if this is a coin flip, a perfect test would go straight up here and then would go all the way up here. And so the area under the curve represents better and better tests. So possible reasons that this happened and possible future directions. Probably the biggest one is, I would say even with 4,500 or 9,000 new labels, the comparison was 2.4 million patches, and I was hoping that these were the least confident ones, and that it would have an outsized effect on the model. But unfortunately, it didn't change much. And so having more new labels, so maybe getting Mechanical Turk or just getting more people to deliver more labels could help. And then potentially adding redundancy. So if you have even more labels than that, I could say discard labels that not everybody agrees on, for example. I could use less original labels, so I could just use less of them and see at which point the new labels improve things, if at all, or I could use none. And I could say, instead of using some kind of semi-experts, I could say the only labels that are going to be used are just completely de novo ones made by non-experts or the original annotations. And just see if I approach anywhere near accuracy of the expert annotation. I could use more training. I could potentially have a pathologist go and train people or create a presentation on how to identify these things. Or I could use or find an easier task for some supervision. For example, there'd be a lot of radiological applications like looking at x-rays or CT scans that I bet would be a lot easier than this task, less fine-grained at least. And then the last thing would be, and some people did this with this data set, is to add supervision at different zoom levels. So this is like almost completely zoomed out here. This is tumor area, which may be more obvious at a more zoomed out level than as zoomed in as the model sees, and then as subsequently the additional annotation sees in those patches. That is it. Any questions?
I've got one question, Scott. You mentioned 4,500 like new data points basically put in. What was that being added to? How many was the pool?
2.4 million.
Was there any way that those ones were weighted more, or? Go ahead.
No, they weren't. I suppose, yeah, I could do that. I don't know technically how to do that, but like within the model that was used, but that would be a good idea.
Yeah, it just seems like even if they were very like the new ones were huge improvements on the old ones, it just seems like, because what 1,000 is 0.1% of a million or something. So it's the data set didn't change too much. I guess it was only the questionable ones that were the ones that were changed, but it just seems like it's a very small amount.
It's true. Yeah, there should be a better way for me to get more data, or to effectively get more data. Like I'm thinking if I were to use a higher zoom level as well, it could potentially like triple or more the number of patches as well. Anyway, that's a good point.
Or instead of using the full 2 million, use just a subset of that as the baseline.
Yeah, that was what I meant about using less original labels, for sure.
Oh, got it.
Hi, Scott. So in terms of doing the actual labeling of the patch, at what percentage of cancer do you want to label it as cancerous, I guess? Because like, I think we've all seen the CAPTCHA where we're trying to label which squares contain cars. And there's like a portion of the car's antenna that sticks up in one square. We're never really sure. I mean, is that part of the car? Kind of. Should it be the car? I don't know. So this is kind of the same feeling, right? Or like shrink the size of the square to the size of the cell kind of idea.
I don't know the answer to that. I'm not sure if anybody knows the answer to that, like what the optimal amount is. Like there's a case to be made to say that even a single cancer cell is important to pick up, because ultimately having a very sensitive model is probably more important for practical purposes than having a very specific model. If you can have a model that picks out 100% of, like has no false negatives, then that's probably more useful to a pathologist, because you're not just going to let this model get out there in the real world and make the final diagnoses. You want to ideally be able to exclude completely normal ones to allow pathologists to focus on edge cases and not miss anything. But I don't know necessarily if that means that even a single cell is really important to be classified as malignant or not.
Cool, thanks. Just a quick follow-up. I've heard, and I've never looked this up or bothered to find out, that cancer exists in most people, that there are cells that are cancerous that are kicking around in pretty much everybody if you look hard enough. Is that true or false?
That's true. They're really, really small. The odds that you would find one in a random lymph node that's being investigated for cancer is very low. And if it picked up single cells at a time, that's also like a special case within breast cancer where the immunological methods of tagging cancer cells has gotten so good that they are finding like they're called micrometastases. And the impact that ends up having on your prognosis is very small, as you would kind of expect. And so there's some level of nuance to it, but it probably doesn't matter for these applications.
Cool, thank you.
All right, thanks.
All right, I think we should end there. Thank you, Scott. Now I'm going to suggest we take maybe a 5-minute break before we come back. So let's see if I can do this. I'm going to try to share my screen here. And now, hopefully, you can see a countdown. So I'll see you all in about 5 minutes. All right. Welcome back. Hopefully you're back. Shruti, who would like to share their screen?
Yeah, that would be me.
Okay.
I will share my screen right now.
Awesome.
Okay, can you see it?
Yep.
Okay, perfect. All right. So I'm really excited to talk about this project. Just a second. Let me just minimize my screen. Yeah, perfect. It is titled Ransack, and it is going to be, we are going to be talking about an algorithm that is going to be used to combat noise in active learning. Sorry, just a second. Yeah, this is how the slides are going to be paced. There'll be the introduction and the problem statement of what we actually hope to accomplish and we actually did. And there's going to be the related work, the data sets the data set that we use. There's going to be the system architecture, and there's going to be the intuition behind the algorithm, like how the algorithm works and how we implemented the algorithm to combat noise in active learning. Here's a disclaimer. The algorithm was not actually invented by us. It is going to be used by us to combat noise in active learning. And this hasn't been done before. And there's also going to be the results. All right. So usually in traditional machine learning systems, there's the supervised learning, unsupervised, and the semi-supervised. The problem with supervised learning is that you need a lot of labeled data in order to make sure that the learning algorithm actually learns well. So, but the problem is, again, for most of the tasks, we don't have enough labeled training data. And there are some disadvantages associated with unsupervised and semi-supervised learning as well. And so over the past decade, human in the loop approaches have been used to combat this. So that basically means you have a small pool of labeled data and a large pool of unlabeled data. And in active learning, the learning algorithm basically chooses points that are close to the decision boundary and queries the oracle for the labels. So the oracle can either be a human expert or another system itself. And so the problem associated with active learning is that the learning algorithm takes the word of the oracle to be the final word. So that basically means that sometimes the human himself or basically the oracle might not be sure of the labels that it's giving the learning algorithm. And for example, especially in the medical domain, if you look at a CT scan of lung cancer, it's kind of sometimes in some cases it's kind of hard to identify if the tumor is malignant or benign. And in such cases, especially in the medical domain, it is very difficult. Also, you can use non-experts to do this, but you might not get very reliable labels for some of the cases. So this is active learning. Like, there's this machine learning model. Let me find my pointer. Yeah, there's this model, there's an unlabeled pool, then the learning algorithm takes data points from the unlabeled pool to be queried and adds it to the training set. And it keeps building upon its training set and improving the model. So like I told you, the problem is that the noise associated with active learning is a lot. So what we are doing is we are trying to find an algorithm that trying to form a system that would improve even with noise present in the labels. And for this, we use the Varshini will be talking about the related work and the data set. Yeah, over to Varshini.
Am I audible?
Yep.
Yeah. Okay, so for related work, we focus particularly on approaches that try to combat noise. I will highlight the answers to the following questions now. One, what are some challenges faced by an active learning system that queries an oracle? Two, were these challenges always addressed? If yes, what are some solutions? And finally, do these solutions always work? To answer the first question, a strong assumption in most active learning research is that the quality of label data from the oracle is high, but this is always not the case. Labels from empirical experiments or even labels from human experts might sometimes be unreliable. The reason could be some instances are difficult for both humans and machines. And there are also cases where people tend to become distracted and fatigued over time. This could reduce the quality of their annotations. All these factors could result in noisy labels. So this is the challenge that we chose to address. And to address this problem, some approaches have used crowdsourcing tools such as Mechanical Turk and online games to essentially average out some of this noise by cheaply obtaining labels from multiple non-experts. But does this always work? Can we always trust non-experts? No, I wouldn't. So there are some complex tasks, right, where we need the presence of a domain expert, and that becomes important. For instance, as Shruti said, in the medical domain, that becomes important. Moving on to some other solutions, some approaches have tried to relax the assumption that the oracle's labels are always trustworthy. Other reasons work also assumes, I think you can move on to the next slide, Shruti.
Yep.
Other reasons work assumes that a learner may repeat queries to be labeled by multiple annotators. However, this system was uncertain about when the learner could query a new unlabeled instance and when to query repeatedly in an attempt to denoise an existing but suspicious training instance. Moving on to the data set, Shruti. Just a second.
All right, so I think there's a problem with her connection. So moving on to the data set, we chose the EEG data set from, I forgot that. Let me just check back.
Yeah, I'm back.
Hey, Varshini, you're breaking up. Yeah. Okay, perfect.
Is it better now?
Yeah.
Moving on to the data, we use the benchmark data set for the IC classification problem. So it consists of EEG signals recorded from 14 different electrode positions, recorded with the emotive EEG neuro headset. You can see the positions in the image right here. So it contains about 15,000 instances. The isolate, whether open or closed, was captured by video along with the EEG signals. The outputs are represented in a binary fashion. Yep, moving on next one.
Yeah.
Next slide.
Yeah, so I will be talking about the actual architecture of the system that we built. And like Varshini said, we are using the EEG dataset. To be honest, we don't really care about the dataset as well as pre-processing because our main focus is to decrease the noise in active learning. And this method would work for any system focusing on any problem. So, but for the purposes of this project, we are using this EEG dataset. We just did feature scaling to kind of normalize the results, I guess. So it isn't pre-processing technically, but we just did that so that because initially the results that we got were really bad, but once we performed feature scaling on that, they became a bit better. So this is where the most interesting parts come. And we had this baseline of uncertainty sampling, which is the least confidence as well as the entropy sampling. And we use that as a baseline. And then comes our ransack algorithm. And to compare these against each other, we passed all of this training data to a vanilla plain multi-layer perceptron. And this method would work for any classifier because basically this works on building upon the training set. And then just to evaluate the results, we look at the accuracy and the F1 score, F1 score being the main thing. And So over here, the results that we got for least confidence as well as entropy-based sampling for out of 14,000 instances, 0.2% of the data went to the training set, 0.2% of the data went to the testing set. 20% of the data went to the training set, 20% went to the testing set, and 60% of the data, which is around 7,500 instances, they went towards the pool. So as you can see, the results over here, oops, we forgot to add the F1 score, which we added later. So over here, without normalizing, with normalizing, we got 55.5%. And once we performed feature scaling, it was a bit better. We got 80.2%. So by 20% of the training data, I mean around 2,000 instances. And for 2000 instances, we kept adding on, and this is the active learning method. And least confidence, we got an accuracy of 81.2%, and entropy based sampling as well, we got the same. And that's because we did the binary classification. For multi-class classification, the values would differ. And over to Melika, who will explain the algorithm in a better way.
So to understand ransack algorithm better and know how it would work, ransack is removing outliers, and this algorithm starts with reading extracted plain points by the ransack algorithms. Then it can clustering starts with the randomly selected points and search for neighbors of the randomly selected points. Also, its search points distance is less than the given threshold, and add points as a neighbor points, and then finish the ransack algorithm if no non-search points left. As you see in the right side of the picture, that just has one line, putting all the points included, which are less than a given, the distance is less than the given threshold. So next slide, please. So in our model, we made this flowchart. By using approximately 2,000 of 14,000 data, we use 2 iterations as K in active learning. For finishing just for finding most ambiguous data points, then we randomly selected 95% of data. We can send those 5% of data to the Oracle to verify the labeling. Then we have to train and test on 95% of data, and we repeat 10 times to get the highest accuracy with this algorithm. In each round, we had 100 data added to the selected data set, and we had to be consistent for the number of iterations from pure active learning and ransack. So we used 10 times or 10 iterations for both models to compare the results from active learning, pure active learning, and active learning with ransack. And to compare the results, we have used F1 scores to compare those 2 models. And next slide, please.
Sorry. Yeah.
Yeah, thank you. And we put 10%, 20%, and 30 and 40% noise probability in our model to see how the system will work. So obviously the accuracy in F1 score would decrease when we increase our noises. Next slide, please. And also the active learning with ransack get the same results as well. And to compare here, so we got our desirable results, which is pure active learning and ransack. We got higher F1 score in active learning with ransack than pure active learning. So for a future work, we would like to extend this method to other domains where data set is on actually smaller pools of sorry, of unlabeled data as well. And that's the result we got.
Yeah. Any questions? Or is everything a question?
So can you use this on any type of data? So for instance, could we use Ransack on the kinds of images that Scott was talking about in the previous talk?
Yeah.
Go ahead.
Oh, okay. Yeah, yeah. So this algorithm was built with the notion that it could be used on any kind of task, because any kind of task that uses active learning. And our I don't get the word. Okay, our intuition is that it would perform well even on Scott's system. Yeah.
And also we have found that when we increase the noises, so we got better results on active learning with Ransack. So I think maybe it would work for other.
Any other questions? All right, well, Scott.
I was going to ask if those results, if you did any statistical tests on them to determine if, like how different the F1 scores were for Ransack and not.
Oh, no, we didn't do that yet, but we are planning to do it before Saturday.
Okay, thanks.
Yeah.
Cool. Thanks, everyone. And then we can jump into the final presentation. If Pyoyan is here.
Yeah, I'm here. One
okay.
second.
Cool.
Okay. Can you see my screen now?
Yes, we can see your screen.
Yeah. Okay. Hello, everyone. My name is Puyan Liu, and my presentation today is about the investigation of the learning performance of human agent transfer algorithm when incorporating with policy gradient method. During the presentation, I will first give a recall of the human agent transfer algorithm, and then I will raise my hypothesis and talk about my experiment, environment, and design. I will give the results and analysis of my experiment. Finally, I will talk about limitations of the experiment and summarize my project in the last slide. And so, it's not really an introduction, but kind of recall. So what is the HAT algorithm? Formally speaking, according to the original paper, HAT is an algorithm which combines transfer learning from demonstration, and reinforcement learning to achieve rapid learning and high performance in complex domains. So in short, it is an algorithm which uses human demonstration as the guidance to a reinforcement learning agent to achieve a faster learning and a better final performance. It's like introducing some prior knowledge into reinforcement learning, into a reinforcement learning agent to help its learning. So to do this, HAT uses 3 different algorithms to bias the policy of a reinforcement learning: value bonus, extra action, and probabilistic policy reuse. For the value bonus algorithm, it's adding a value to the value function of the human selected action, such that that action is more preferred for the reinforcement learning agent to select. And For the extra action algorithm, it's adding a pursuit action to the action space, which will execute the human selected action when being chosen. For both of these two methods, the agent are forced to choose the human selected action for the first couple episodes. And the last method is the probabilistic policy reuse, where the agent has a probability to choose the human selected action. And this probability decreases with the increase of timestamp and the number of experienced episodes, such that the prior knowledge exerted on the policy of reinforcement learning agent is decreasing, and the reinforcement learning agent can learn by itself when it's approaching to the end of the learning period. So far so good, but what are we going to do in our project? It has been shown that HAT algorithm is robust to noisy and suboptimal demonstrations when incorporating with SARSA methods, which have random exploration. But we're wondering if this robustness remain existing when incorporating incorporating HAT algorithm with policy gradient method, which doesn't have random exploration. The main question we want to investigate is whether the suboptimal demonstration will lead to a convergence to suboptimal policy. As you can see on the figure on the right side, we suspect the human demonstration will initialize the reinforcement learning agent into some point, which will converge to a local optimum if running gradient ascent on this initialization point, compared to like a kind of random initialization, which will possibly converge to the local optimum. And therefore, we raised the following hypothesis. When incorporating with policy gradient method, we believe HAT agent has a better learning performance than the pure reinforcement learning agent when using optimal demonstrations throughout the learning period. We also believe it can initially perform better than the pure RL agent, but has a worse final convergence when using suboptimal demonstrations. We believe this is because the suboptimal demonstration can lead to a convergence to suboptimal, to like a local optimum. To verify the hypothesis, we run an experiment on this extended mountain car problem. The extended mountain car problem is very similar to the normal mountain car problem. The only difference is that instead of having the goal to get out of the mountain, it has a goal to rest on a goal position, which is shown as the flag icon here. So it's having an action space to accelerate left or right or do nothing, a reverse signal of -1 for every timestamp, and termination if it's sufficiently close to the target head with a low velocity. Now we come to the experiment design. Since our experiment is highly sensitive to the optimality and the noise in the demonstration, instead of using real human demonstrations, we're using a autosolver to generate demonstrations of different optimality and noise level. And to be more specific, we're using a reinforcement learning, we're using a softmax actor critic reinforcement learning agent. And for the optimal demonstration, we use the optimal actions from the autosolver. For suboptimal demonstrations, we are kind of limiting the action space of the output of the autosolver. So like for example, for suboptimal left demonstration, we're allowing the agent to only choose the accelerate left or like do nothing. For the noisy demonstration, we assign a probability of n for the reinforcement learning agent to randomly choose some action, and otherwise choose the action from the autosolver. But following this design, we get the following experiment results. This one is for the head agent when incorporating with extra action. As you can see, the head agent has a significantly better performance than the pure RL agent at the beginning part, but it's having a worse performance than the pure RL baseline in the final stage. We believe this is due to a convergence to local optimum. Things get different when we are using probabilistic policy reuse. If not having any significant head agent is not having any significant improvement compared to pure RL at the beginning, at the early learning stage, but it's kind of converging to the same final policy, even though it's like having larger variance than the baseline. So we kind of believe a head agent with probabilistic policy reuse did converge to the optimal policy at the final learning stage instead of the local optimum. When using value bonus method, it's kind of having a very strong instability during the final convergence, but it still showed a better performance than the pure RL agent at the early stage. And now let's go to limitations and the future work. The first one is the unexplainable instability. As you can see, like the value bonus algorithm showed strong instability during the final convergence with all demonstrations. We haven't found a reasonable explanation for this, so this can be done in future work. And also the demonstration limitation. Our experiment was run with only 2 different suboptimal demonstrations. It probably need more runs, like with different demonstrations, to come up with a convincing conclusion. And also the demonstration false limitation. Our demonstration rules were generated from autosolver instead of real human demonstrations. Things could be different when using the real human demonstration. And in summary, when incorporating with softmax actor-created method on the extended mountain car problem, head agent showed robustness to noisy demonstrations, like a convergence to suboptimal policy when using suboptimal demonstrations with extra action algorithm. But it showed strong robustness to both noisy and suboptimal demonstrations when using the probabilistic policy reuse algorithm. A significant better initial performance than the pure RL agent can be found when using value bonus or extra action algorithm, no matter incorporating with any demonstrations. But this improvement is less significant when using the probabilistic policy reuse algorithm. Okay. Thank you. This is my presentation. Any questions?
Why did you use extended mountain car?
Oh, so let's go back to the environment. So the first reason is having a simple physics environment, and we make the change such that it retains like a simple physics environment from the mountain car problem, but has more difficulty to solve. And we believe the policy surface of the extended mountain car problem is more rougher than the mountain car problem. But so we believe more local optimum exists for the extended mountain car problem, and this helps our investigation on the head algorithm's robustness against the suboptimal demonstration.
Thanks.
Yeah, you're welcome.
Did you mention the performance of the noisy and the suboptimal demonstrations?
I mentioned the performance. Sorry, 1 second. I mentioned the performance for the with different with suboptimal demonstrations, and for the noisy one here, this is actually having n equals 0.3, where n is the probability to choose random actions, and the 1 minus n is the probability to choose optimal actions. Yeah, it's actually, I should include another figure to compare the performance of head algorithm with different noise level. I just got the data today, so I haven't made that figure, but I will include the comparison with different noise level in the final report.
Cool, because what I was wondering about is you show the performance with HAT with suboptimal and optimal demonstrations, and I was wondering if it would be easy to just show if I just ran these policies, what is their performance? So is the optimal demonstration getting 200 and the suboptimal one is getting 300, or is the suboptimal one getting negative 3,000?
Yeah. Yep. It's like, yeah. It's like, sorry, are you referring to like the final performance of the suboptimal demonstrations, or?
So not even before you learn in HAT, you collect these demonstrations, and I'm just wondering how good or bad these demonstrations are. So if I look at the optimal demonstration,
you can see at the beginning. So because the extra action was forced to use the action from the demonstrations, like from the autosolver at the beginning. So the beginning curve actually show the performance of the demonstrations.
Okay, yeah, that's exactly what I was looking for. Thank you.
You're welcome. Any other questions?
All right, well, thanks again. I look forward to reading this report too.
Yeah, thank you.
Okay, so let's see. I'm going to go into the main Discord channel. And let's see, it's 12:45 now. I'm going to suggest we have two poster sessions, one 12:50 to 1:10 and one 1:10 to 1:30. Does that sound reasonable? Okay, so that gives us about 5 minutes for a break. And what I would like you all to do is for the projects that did videos, please decide whether you're going in the first slot or the second slot. Try to roughly balance it out. And then for each of these projects, please throw up a link to either a Zoom or a Google Meet that we can use. And if you have any trouble creating that, just ping me. But then once we have a list of the different projects, which meeting rooms they're in, then we can jump in with these different times and you can go and ask poster style questions. And then at the very end at 1:30, I'll hop back into this Zoom and you can briefly tell me how this went. because this is an experiment and this could be a disaster, but hopefully it's fun. So, okay, I'll see you back here, or I guess I'll see you in posters in about 4 minutes. Is that enough time? Do you need more time to get ready? No? Okay. All right, so start dropping links and times into Discord and yell at me if you need any help.